42-inch static mixer altogether. It says 36 inches on there. The 36 inches was for one section, when there was a second section, a 6-inch section located inside the main reaction chamber. And they were both 0.75 inches in diameter. That is an inner diameter. So, how does it actually mix? These helical elements produce striations. Basically what happens is when the flow enters into the static mixer, it comes in contact with the first leading edge of the static mixer, which divides the flow into two striations. Now, as you go from one end of the static mixer to the other end, the flow is constantly divided as it encounters the leading edge of each helical element. You can see the figure on the top, and go back and describe the equation real quick. The equation S equals 2 to the n describes the number of striations which are produced by the number of helical elements that you have. So in our case, we had a total of 41 helical elements. That means 2 raised to the 41st power, which comes out to 2.2 times 10 to the 12 striations. Yes, a lot of good information. So if you look at the figure, 14a indicates the first helical element. So 2 raised to the 1 equals 2. So you see 2 striations that are formed. The second, 14b, shows 2 raised to the 2, the second helical element. So 4 striations should appear. So you have 2 red and 2 green, as seen right there. Now, as you continue along, as you can see with more striations that are produced, it becomes very difficult to actually distinguish between the striations, which is what you want, because you want a good quality mixture, especially when you mix methoxide and the triglyceride, because they usually don't want to mix together. So with the 41 helical elements, the number of striations that you produce will produce a good quality mixture. So let's talk about the actual structure of the static mixer.
Can I ask a question about your last slide?
First time. Okay, so going back to the structure of the static mixer. So static mixers can be made of metal and they can be made of plastic. It really just depends on the type of chemicals that you're using altogether. We chose to use PVC. We had kind of come up with the idea, maybe using metal, but that didn't factor in because of budget, so we went for PVC. PVC is an amorphous structure, which means it doesn't have a crystal structure and a long-range mortar to it. It's single bonded with a chlorine atom, which means it is very, it's able to resist acids, bases, alkalis, and most inorganic chemicals, which means it's very good in this situation with the chemicals that we are using. The melting point of PVC is 176 degrees Fahrenheit. As Will stated earlier in the presentation, I think the highest temperature would go at like the 122 degrees Fahrenheit, so that's well within the acceptable parameters that we need for this. So I will now pass it off to Brian, who's going to talk to you about the design specifications.
Thank you, Gabe. To start, the design specifications went through many processes throughout this semester and last semester. Since the main goal is to find the most efficient angle and separation efficiency, we had to create a rotating system to find that angle. And we want to keep it simple and efficient. So to start, we started out with the handle where we were able to slide the reactor, which is the glass tube, in between the 3 rings here, where we would then clamp down with some rubber feet to center the ring between the supports so it doesn't touch, and then allow for the reactor to sit comfortably inside it. Now, this stand or handle needed to be stable for the reactor as it moved through the process, or through each angle, and since the angle stayed once we started the reaction, we were able to lock it in place. So there's no rotating parts about this during operation. So the stand itself became a basic door frame to support the handle and allow for the easy rotation. The door frame stood about 6 feet tall, since the reactor itself was 46 inches tall. Now that also leaves room for the pipes to come in and out for each input and output of our chemicals. The stand itself is made out of wood due to time crunches and a late redesign that happened in early November.